All right, a little bit of a trip down memory lane here for factoring. We know that factoring is the same thing as division. And you always look for a greatest common factor first, and I should back up. 6v plus 10. Now, if you're saying division, remember that you're literally just dividing these things by that GCF to see what's left inside. So, always look for a GCF first. I mean, you may not have one, but at least you can look for one. This one has 8 and an x in common. So you're basically dividing these by 8x. It's always a sad day when you have an x in common with another person. So that would leave me with x plus 6. So these are my first two answers. And the next one doesn't have a GCF, so we can go straight to factoring two binomials. Now, so they have to multiply together to give me 8 and add up to 9. My factors of 8 are 1 and 8. And the other option would be 2 and 4. 3 does not go into 8, therefore I know I'm done. Now, I don't know if you noticed, but I followed kind of a V-shaped pattern with my factors when I know they're getting closer together, and I know that I've run out of options. So 1 and 8 is obviously the choice we want. They both have to be pluses in this case to add up to a positive 9. No GCF in this one, but this one is called a difference of perfect squares. Difference obviously meaning subtraction, and obviously perfect squares. Now, there's a middle term which is missing. So another way we could write this is x squared plus 0x minus 16. And if we thought about multiplying to this and adding to this, then it would make sense to us that one has to be positive, one has to be negative, and since they have to be opposites of each other, it would have to be 4 and 4. If you run across one that does have a GCF, pull it out, just like we talked about on the other questions. Oh, look, there is a difference of perfect squares, so we could go farther. Of course, the idea of a square is in that you take the square root. And the square root of 25 is 5. One's a plus, one's a minus, and you're done with the question. So, pretty straightforward, not too complicated. Now, what happens if you don't have a GCF and the linear term at the beginning, or the quadratic coefficient, is not a 1? Well, my favorite way to handle this, I mean, yes, you can guess and check, which there's a lot of teachers that will, force you to guess and check. But I like the Berry method. So this is going to look like a double magic trick, so hold on. I'm going to pick up that 6 and I'm going to multiply it times the 2. So it looks like there's a magic trick where I just made the 6 disappear. And then factor this like normal, so x plus 3, x plus 4, normal stuff, right? Multiplies to 12, adds up to 7. Well, at that point, then the 6, which magically disappeared in the beginning, reappears in front of both of the x's. Now, what is 6x times 6x? Well, that's 36x squared. Well, that's way too big. Way too big. So, what that means is that we have introduced greatest common factors that need to be removed. Look inside the parentheses and see if there's something that can be taken out. Looks like I can take out a 3 out of that one, which would give me 2x plus 1. And in this next one, it looks like I can take a 2 out of that one, 3x plus 2. And guess what? Now I have my factored form of the original. No guessing and checking. It's called the Berry method. Guy with the last name of Berry came up with it. But looks like a double magic trick. You must, however, make sure there's no greatest common factor before you do that trick. Now I know most of you see that there's a 3 that goes into all of these. I'm going to suggest that you make it a negative 3, which would be 2x squared plus 3x minus 20. Now, got rid of the GCF. Now it's time for the Berry method, right? Now, my final answer is going to have a negative 3, and it's going to have 2 set the parentheses. But let's just worry about the part in the parentheses first. So, if I take the 2 and I drop it on the constant at the end, that's x squared plus 3x minus 40. Now I can sit there and factor it and go x plus, x minus, because you have to have one of each to get negative 40. So my factors of 40 are 1 and 40, 2 and 20, 4 and 10, 5 and 8. I don't think anything else goes in 40. So, looks like this is a job for 5 and 8. 8 goes with that one, 5 goes with that one. So that when you add them together, you get positive 3x in the middle. Well then, that 2 that magically disappeared at the beginning is going to reappear in front of both x's. And I look for GCFs that I can pull out and get rid of. Looks like there's a 2 I can pull out of that one, leaving me x plus 4. Looks like nothing can be pulled out of that one, so 2x minus 5. So that's my final answer on that. And you can't forget the negative 3 that's out there in the front that you took out at the very beginning. Okay, so do we want to solve this by factoring? I don't know, does this thing factor? Let's double check here. B squared minus 4 times A times 6. Okay. So yeah, that's 49. It does factor.
33 in front of the auditorium. Sophia Kogar. Thank you.
So this factors into x minus 4, x plus 3. And then that 6 comes back, 6x minus 4, 6x plus 3. And now I can take a 2 out of that one, 3x minus 2, and take a 3 out of that one, or no, 3, yeah, I was right, 3 out of that one, which would be 2x plus 1. Keep in mind that's equal to 0. So, if you have two things that multiply together to give you 0, what do you know about one of those two things? Either this one's 0 or this one's 0. That's what you know. So either 3x minus 2 is equal to 0 or 2x plus 1. And so now you can solve those things, 3x equals 2, x equals 2/3. 2x equals -1. X equals -1/2. Oops, missed a question. Push this to the other side, 8x squared minus 10x. Okay. Let me just double check this. B squared minus 4, 8. Yeah, that's perfect square. Okay, that does factor as well. Okay, so we could use the Berry method again. So the 8 comes down on the 3, x squared minus 10x plus 24. X minus 6, x minus 4. The 8 comes back in front of both x's. Then I look for GCFs that I could pull out and throw away. In the first one, looks like I can throw out a 2, so that'd be 4x minus 3. And in the second one, looks like I can throw out a 4. So now I can set my two factors equal to 0. 4x minus 3 equals 0. And 2x minus 1 equals 0. So 2x equals 1. X is 1/2. Whoops. I take the 3 to the other side. 4x equals 3. Dividing out the 4, the other x value is 3/4. Gotta figure out what they're thinking here. Okay, to solve this, to push everything to one side and just say 2x squared minus 36x plus 157 equals 0. Does that factor? So, to solve this, now if we think about it as a polynomial, we could do y1 equals this polynomial, and y2 equals 0, and see where they cross. Or we could simply do the first one and look for zeros of the polynomial. Now, it's true we could use a quadratic formula on this. I do the discriminant b squared minus 4ac. I get a discriminant of 40. Remember b squared minus 4ac? Let's see here. 40 goes under the radical, plus and minus. We've got opposite of b all over 2 times a. If we're looking for exact values, that'd be 36 over 4 plus or minus. Square root 40, that'd be 2 radical 10 over 4. So we could simplify this to 9 plus radical 10 over 2. Now that gets you the exact answer. If you're trying to do the polynomial method, you're going to end up with a decimal. Like y equals, clear these things out, 2x squared minus 36x plus 157. And we're going to graph this and see what we end up with as far as 2x squared minus 36x plus 157. And you can see our picture right here. We're looking. So we got our picture here. But the best thing we can get are decimals. Graphing is not going to give me a nice, awesome solution like this. So the idea of of using the quadratic formula is the best way to get the nice one. So I think that's the best way to look at it. Unless you need decimals, and then if you need decimals, you could go that route. Because there they are, 7.42, 10.58. All right, see you in class.